Hello, we've been getting some questions about number 36. Actually, let me label this problem here. This is a problem that should be very similar to number 36 from your assignment. In fact, the only thing that really changes is the values in A and B might be a little different. So this problem asks about the demand for tenths. And it starts out by giving us a demand function. For sportsman, 5 by 7 tenths. The function p equals negative 0.01 x squared minus x plus 40. P is measured in dollars, and x is measured in units of 1,000. And this is a common way for us to see these demand equations. So I need to make a few comments about how this function's structured, and then we'll talk about how to do these calculations. The challenging part here is that they've mentioned that x is measured in units of 1,000. So that has implications for how we do the calculations. You'll notice in part A, they mention 5,000 tenths and 5,050 tenths and 5,010 tenths. So those are actual tenth numbers. X is not measured in actual tenth numbers. It's measured in units of 1,000. So when you work on this problem, if you see 5,000 tenths, I spelled tenths wrong, 5,000 tenths, that actually means that implies that x equals 5. If you see 5,050 tenths, that actually implies that x equals 5.05. And then you can see we also have to do, I think it's 5,010 tenths. Oops, that is not how you write 5,010. So that implies that x equals 5.01. So these blue numbers are the values, the x values that we're going to use when we do our calculations. Now the other thing that I want to point out here is that letter A is asking for average rate of change, and letter B is asking for what we call instantaneous rate of change. And I know that because they're only giving me one x value here. They want to know the rate of change at 5,000. Whereas letter A wants to know the average rate of change between 5,000 and 5,050, or between 5,000 and 5,010. So average rate of change is a different calculation. I like to think of average rate of change as similar to the old slope equation that we used to have in school. So if you remember, you may have heard of this equation, m equals y2 minus y1 over x2 minus x1. That's essentially the equation that we're going to use for average rate of change. We make it look a little fancier when we're in calculus class. Instead of writing it y2 minus y1 over x2 minus x1, we'll write something like this. F of x2 minus f of x1 over x2 minus x1. That's how we're going to write that. But it really just means this slope equation over here. Now, what that means for us is we have to do this calculation, and we're actually going to do two calculations, but it'll look like this when we write this out. So for the first part of letter A, I'll call that A1, we're going to need to do the calculation f of 5.05 minus f of 5 divided by 5.05 minus 5. So the first x value is 5, right? 5,000 tenths. The second x value is 5.05 because that's 5,050 tenths. So we replace all these x1s and x2s in the formula here with our values that we need. And then our job is to figure out what this equals. In the same sense, we'll do the second part, but we'll do 5.01. I'm going to run out of space here. Minus 5 divided by 5.01 minus 5. So f of 5.01 minus f of 5 over 5.01 minus 5. All of these, or both of these, are just old school slope calculations with a bunch of fancy numbers. And again, our job is to get the answer to this thing. So on the next slide, I'm just going to show you one way that you can quickly get these values just by typing some stuff into Desmos. I'll also explain what it really is that we're doing when we're figuring out these values. And then toward the end of the video, I'm going to run through a calculation for letter B, which is this rate of change. And right now, we're still using the four-step process to find that rate of change. So that's going to be a little bit of a lengthy calculation. Okay, enough of this slide. Let me show you this neat little trick with Desmos to do these calculations. By now, you know that I like to use this Desmos graphing calculator website to do a lot of calculations. You can draw graphs of functions, but you can also do a lot of calculations. So just take a look at what I've done here. I went ahead and I entered in the function just like it showed up in the problem. F of x equals negative 0.1 x squared minus x plus 40. Then I made some variables, x1 and x2. x1 I made 5.00, that's our 5 there. And x2, 5.050, that's our 5050 number. I had it compute the y values, right? F of 5 and f of 5.05. And you can see those values here. Oops, I'm drawing on the screen. Let's get rid of that. You can see those values here. Oh, goodness. Okay, now it's letting me play. So those y values here. So when I plug in the 5, I get 32.5. When I plug in the 5.05, I get 32.39975. And then here you can see my slope calculation. I called it M1. I did f of 5.05 minus f of 5. That's the y2 minus y1 over x2 minus x1. And I just type this in, and the answer just pops out there. So the first value that we should get is negative 0.05. And then I went ahead and made another value, x value, 5.01, and I plugged that into the function, and that value came out to be 32.47999. And then I did the slope calculation again. I got negative 0.01. So those are my two calculations that go along with those values or those equations that we wrote out on the last slide. Now let me show you something over here so you can kind of see what it is that we're actually calculating. If I zoom in on these values, basically what we're doing is we are connecting these dots, and let's see if I can stretch this out a little. It didn't work as well as I'd hoped, but here's the 5 value, x equals 5, that's this guy right here. Here's the 5.05 value. What we're doing is we're connecting those dots and then just computing the slope. And then for the second calculation, we do the same thing, but we bring that point closer, right, to 5.01, and we're making that calculation of the slope between these points, right, if we just connected them with a segment. So we were just calculating slopes when we did those calculations. The last part of this problem, part B, wants us to find the instantaneous rate of change. And for that, we have to use our four-step process with our derivative. Okay, enough talk about this graph and these calculations. Let's go back and write out some answers. So for part A, the first one, we came up with a calculation, I think it was negative 2.005. And that is dollars per 1,000 tenths. And then for A2, we did the calculation and we got negative 2.001. Finally, for part B, let's do that in yellow. For part B, they're asking us for the rate of change when the quantity demanded is 5,000. And for that, I need to run through that four-step process. Since we haven't officially learned derivatives at this point, the shortcut rules, we're going to do it the long way, which is fine. So remember to do this calculation, I'll just call this B1 because there's only one answer there. We're going to do the limit as h approaches 0 of f of 5 plus h minus f of 5 over h. We're going to calculate this limit. That's an h there. I got to write a little neater. Good news is I have a few of these values already. So f of 5 is, that's our 32.5. So let me just make a note over here. Okay, and then we'll write this out and we'll see if we can get this limit. So it's going to be the limit as h approaches 0 of negative 0.1 times 5 plus h quantity squared minus 5 plus h plus 40 minus 32.5. And let's multiply this out. And I'll probably have to go to the next slide to finish this off, sorry. This is going to be negative 0.1 times 25 plus 10h plus h squared minus 5 minus h plus 40 minus 32.5. Oops. Getting sloppy here. I need to start on the next slide. Okay, so I'm going to transfer this over to the next slide and finish this off and hopefully write it a little neater. Okay, so I've picked up where we left off. I did distribute that negative 0.1 in that first expression, so we end up with this calculation, and now a bunch of great things are going to happen. I have the limit as h goes to 0 of, so check this out. Believe it or not, but negative 2.5, negative 5, and negative 32.5 add up to negative 40, and that means it cancels out with that 40. So the next part of this looks a lot cleaner. On top, in the numerator, I'm going to have negative h minus 0.1 h squared, and then another minus h, and on the bottom I'll have h here. And then what I can do is I can factor out an h from this top part. And if I do that, that makes this a 1, that makes this a negative 0.1 h, and that makes this a 1. And that's good news because now these h's cancel. And so the answer to our question B is going to be just the limit as h goes to 0 of, well, negative 1 and negative 1 is negative 2. And then we've got minus 0.1 h. And since I'm sending h to 0, right, I'll use substitution on this limit, and the value comes out to be negative 2. And that was almost expected. I sort of knew it was probably going to be negative 2 because those other values we had were approaching negative 2, right? When I did the first calculation, it was negative 2.005. And when I did the second calculation, it was negative 2.001. Oops, too many zeros there. Negative 2.001. So as we move those points closer together, these slope calculation values were getting closer and closer to negative 2, which is what we ended up with. So that's a long-winded and very terribly put together description of how you attack number 36. I apologize. I was rushing to get this done to answer some questions, but hopefully it helps a little, and maybe I'll have time to clean this one up later. But for now, we'll take it for what it is. I hope this helps. You know where to find me if you need me. In the meantime, take care.